structure, and algebraic structure can be a group or a monoid or an algebra. So let us see in the context of algebras, let us see what this dimension is and why is it useful. So let's start with an affine algebra over a field K. Affine means that it is finitely generated. So there is a generating set which generates the algebra. For example, if you think about the matrix algebra over a field, we know that all the elementary matrices they generate the algebra. Now, given an algebraic set, the generating set of an algebra, it naturally defines a filtration of the algebra. By that I mean some kind of increasing sequence of subspaces in the algebra. Okay, so what is this sequence of subspaces? The first term is a field which is sitting inside the center of the algebra, as you know. Then there is the linear span of the generators. So this is the linear span of the generators, and then we take powers, successive powers. Now, it's just for convenience, we may add the unit element of the algebra to this generating set. So this is why I have written. These are the generators, and I've added one generator to it, which is just the unit element of the algebra. Now, so this defines the sequence whose first term is the linear span and the second term is the square. Okay, so for example, let me take this polynomial ring Kx, x is the indeterminate. Now, as you know, it's generated by this one variable x over the field K. Now, so this is a very simple example. Let us take Kxy, whose generating set is x and y. So it's generated by x and y. So I write this filtration. I begin with k, and the second term is kx plus ky plus k. So what is this? This stands for the subspace generated by, which is a span of x, y, and 1. Now the third term in this filtration is just this thing squared. Okay, if I square this thing, what I get is the span of all the words in x and y. If you understand what I mean by words, I just mean that monomials of the form x to the I, y to the j. So if I square this, I get all the words whose length is at most 2. So there is a very clear meaning to this filtration, that is that the nth term of this filtration is nothing but the span of all the words whose length is at most n. Okay, so now what we are counting here is what is the dimension of the space of subspace of the words which have length less or equal to n. So in the case of this polynomial ring, you will find that for this it is 3, and in general it will be if you look at all the words of length less than or equal to words of length less than or equal to n, the dimension of the subspace spanned by these words will be n plus 1 choose 2. Okay, Now, so we define the growth rate of the algebra by this expression, and this growth rate is called the Gelfand Kirillov dimension. So the growth rate is defined as lim sup of the sequence of logarithms to the base n of the dimension of the nth term in this filtration. So in the case of the polynomial algebra, this dimension is n plus 1 choose 2, and if you expand it out, you will get a polynomial in n of degree 2, and if you take the lim sup of that, you will get 2. So in general, if you take polynomial ring in s variables and you compute the GK dimension, it will be equal to s. Okay, so now this raises at once is, so you know, in this dimension, as you might have heard, this is quite useful in non-commutative rings in particular. Because for commutative rings and commutative algebras, we have another dimension. It's called the Krull dimension. Now, what is Krull dimension? It's particularly suited to affine commutative algebras, and it has a motivation from geometry. So, if an affine commutative algebra is the coordinate algebra of some affine algebraic variety, the Krull dimension is the dimension of that variety. Okay. So, but in non-commutative situation, there are lots of examples of important algebras for which this dimension will not make sense, because this dimension is the Krull dimension in the case of commutative algebras is defined in terms of lengths of chains of prime ideals, and in the non-commutative situation there are a lot of rings which are simple, and so they don't contain any ideals, proper non-trivial ideals. So the Gelfand-Kirillov dimension is important for studying non-commutative rings. Now, a key point about this dimension is, which is a good thing, and which accounts for its usefulness, it is that it does not depend upon the choice of a generating set. So as you know, in general, an algebra or a group can have several different generating sets, and the definition that I've given is making use of a choice of a generating set, but it turns out that it is independent of such a choice, and so it's an invariant of the algebra or monoid or group in question. Okay, now suppose that our algebra A is finite dimensional. So dimension of A over K is finite, then the Gelfand-Kirillov dimension is 0. So in other words, finite dimensional algebras are our base point for the Gelfand-Kirillov dimension. Then we can look at what are the algebras which have Gelfand-Kirillov dimension 1 and so on. Now there are some basic results. The first one is that for any affine algebra A, which is not finite dimensional, GK dimension will be at least 1. So it means that if the algebra is finite dimensional, it will stop growing, and so Gelfand-Kirillov dimension, which is the asymptotic growth rate, as you can see, it will be 0. If it is growing, if it's not finite dimensional, if it's infinite dimensional, it will be at least 1. Then there's another theorem. It's called Bergman gap theorem. It says that if the algebra A has GK dimension greater than or equal to 1, then either it has GK dimension equal to 1, which means it has linear growth. So the example of that is this polynomial ring Kx, or it has GK dimension at least 2. So in other words, this is quite an interesting theorem. So it says that between 1 and 2 you cannot find any growth rate like this, as in the sense of this definition. Okay. Now,
so the global, it has to be an integer?
not always.
But only between 1 and 2, it's not going to, there is nothing that has the global dimension.
Yes.
Okay.
So,
Only for 1 and 2.
if your example is commutative, then how it's related to two dimensions?
Okay, so suppose your algebra is commutative, then it coincides with the dual dimension. Okay. So now this dimension, even more basic concept is a concept of growth. Basically this dimension is quantifying growth. And what is growth? So as I said that for an algebra we can write down this filtration and look at the sequence of dimensions, and we can see how is it growing. It may be growing polynomially because this sequence is nothing but a function from n to n. The sequence of dimensions of the filtration, the subspaces in the filtration is a function from n to n, because for every n I can get the dimension of this a1 to the n. So this assignment is nothing but a function from naturals to naturals. So for such functions, we can consider what is the growth rate, and in this, to facilitate this, we can define an equivalence relation to group together those functions which have the same growth. So let's say fng are functions from n to n, and they are integer constants c and m, which are integers, such that f of n is less than or equal to c times g of mn for sufficiently large n. Then we can say that, so this is actually defining kind of partial order. If this holds, then we may say that f is less than or equal to g, and if the converse holds, then f and g are equivalent. Under this equivalence relation, we have there are lots. We can find that particularly interesting growth rates are the polynomial growth rates. Polynomial growth rates and the exponential growth rate. So polynomial growth is, as you would expect, is just n to the s, where s is some real number, and exponential growth rate is 2 to the n. So I write 2 to the n here because if you take any other base, so if you even take e to the n and 2 to the n, there will be different growth rates, but so far as GK dimension is concerned, they will give you the same they will be equivalent as growth rates, in fact. So these are some important growth rates. As you would expect, that the free associative algebra, affine free associative algebra on n generators, it has exponential growth, and the polynomial growth is defined. Polynomial growth is said to be polynomial if so there are two concepts here. Polynomially bounded growth and polynomial So what is polynomially bounded growth? It means that um, the sequence of dimensions satisfies the inequality, satisfies this inequality. And polynomial growth is when it is equivalent to some, so this is just less than or equal to, and it's polynomial when it is actually equivalent to some polynomial function n to the s. So if it's equivalent to n to the s, it's polynomial growth. Okay, so there is an alternative definition of this dimension, which can be shown to be equivalent to this by means of some basic calculus. It is this given by this infimum. In the case, this is polynomial bounded growth. So I have already given the example of a polynomial ring. For the Weyl algebra, in Weyl algebra over field K is equal to 2n. So in this context, it's good to point out that if the algebra whose GK dimension we are calculating has a filtration with respect to which the associated graded algebra, it's a commutative algebra. The GK dimension is particularly well behaved, and it turns out that the GK dimension of an algebra and the associated graded algebra are equal. So in the case of Weyl algebra, the associated graded algebra is just the polynomial ring in 2n variables. So its GK dimension is 2n. For the universal enveloping algebra, for Lie algebra, it is equal to the, so this G is a finite dimensional algebra, then UG is affine, and GK dimension is just the dimension of G. Okay, so now it's sometimes useful to study representations, and for representations we can talk about GK dimension. So I'm going to talk about, so I'm going to, M will be a module over M, which will be finitely generated. I can talk about the GK dimension of M. So first, I know that it's finitely generated, so I just define M naught, which is a subspace of M, to be the span of the generators of M. So it's this, and now, as in the case of the algebra A, it doesn't matter which generating set for M I pick, because it turns out that this asymptotic growth rate. So we have to remember that the sequence of dimensions that we get is very much dependent on what choice of generating set we pick, pick. But the asymptotic growth rate, which is what we call the GK dimension, it doesn't depend upon such a choice. So so I'm justified in assuming any generating set here, and then we define a filtration, filtration inside M, which is going to be a filtration with respect to this algebra A. So M is in this case, M is an A module. M is an A module. M is an A module, and we are defining a filtration inside M. This is given by the sequence M naught, which is just the span of the generators. The next term is M naught A1. So we remember A1. A1 was just the span of the generators of A, so it was sum KAI. Okay, so this is, and the next term is M naught A1 square, and the filtration is defined in this manner. So it's called finite dimensional filtration because every term here is finite dimensional. Because this is because this M is finite dimensional, M naught is finite dimensional over K, and each AI is finite dimensional. So this is also finite dimensional. Now, as we did in the case of algebras, GK dimension is defined as asymptotic growth rate of this sequence of dimensions. And it will always turn out to be between 0 and the dimension of the algebra, GK dimension of the algebra. So the GK dimension of M is always bounded, so it always lies between 0 and the GK dimension of the algebra. Or suppose we know that the algebra is polynomially bounded growth, then we can also use this alternative form. Now, there's another, so when we talk about GK dimension, it's also good to talk about Krull dimension in the non-commutative sense, and which is defined on non-commutative rings, and which is defined as in terms of the so the Krull dimension is defined for a module over an algebra A. Let's say M is an A module. So it's defined on the lattice of submodules of M, and it measures the deviation of that lattice. For example, if we know that this M module satisfies ACC, then the Krull dimension is defined Km is equal to 0. If it does not satisfy ACC, so we can also say that if M is trivial, if it's 0, we can define Krull dimension to be minus 1. M is 0. So K of M is minus 1. If it doesn't satisfy ACC, sorry, not ACC, it's DCC. So it satisfies DCC, then we define the Krull dimension of M to be 0. Otherwise, we consider the lattice, and we see that if omega opposite, so this omega is a transfinite first transfinite ordinal, if this embeds inside Lm, so we can say that if M does not satisfy DCC, then we know that this omega opposite is embeds in Lm. If omega opposite embeds in Lm and omega opposite square, it does not embed in Lm, so this does not embed in Lm, then we define the Krull dimension to be 1. So in general, we consider Lm and we see if omega n opposite n, if it embeds in the lattice of submodules of M, then and omega opposite n plus 1 does not embed, then we define the Krull dimension of M to be n. And in general, a module may not have a Krull dimension, but this, and also if you want to compute the Krull dimension of a ring, we simply consider the ring as a module over itself, and then we can talk about its Krull dimension. But in general, this dimension is difficult to compute for rings, and one of the applications of GK dimension is to calculate this dimension. I was talking about GK dimension of modules, Gelfand dimension. I just defined it, and now I want to give some examples and give some further explanation before I discuss some important applications. So for module M, I denote by GKM, it's GK dimension, and so if I have an algebra A such that M is a module over M is a module over A, then I know that GK A bounds the GK dimension of M. Okay. Now, So the question is, suppose that M is finite dimensional. M is finite dimensional, then its GK dimension is 0, and that is easy to show. M is a free module, so it's a finitely generated free module, A to the n. Then its GK dimension is equal to the GK dimension of A. But in general, if it's finitely generated, it will be some quotient of An, the regular module, there are n copies of the regular module. So it is some quotient, and is isomorphic to this. And therefore, GK dimension is well behaved in the sense that with this, so if you take a quotient of a module, it will be if I take an exact sequence of modules, then I always have that GK dimension of M is always greater than or equal to the supremum of GK dimension of N and GK dimension of the factor. Okay, so in this case, if I take a finitely generated module, it means that its GK dimension is somewhere between n and 0. Now, so for the Weil algebra, I think define it somewhere. Okay, let me define this ring, which arises in quantum physics. If I take K to be any field, this ring is A and K is the ring generated by variables x1 up to xn and y1 up to yn. So these are the generators of this ring A and K, and the relations are yixj. So this is the Lie commutator. This means yixj minus xj yi. So this notation simply denotes yixj minus xj y, and that is the Kronecker data. So this is this algebra is basically this is a nk because I've used n variables here, and it is the tensor product of algebras. Or I can say n-fold tensor product of first Weil algebra, A. So you can either think of this as being defined by these relations, or another approach is that we take this algebra A1, which is generated by two variables x and y, subject to the relations. So it's subject to the relations xy minus yx is equal to 1. Okay, so this algebra, as you know, arises in quantum physics. Okay. Now this this is the first Weil algebra, and the nth Weil algebra simply n-fold tensor power of that. And for this, as I already mentioned, the GK dimension is equal to 2n. So the GK dimension of this has GK dimension 2n. Now we can ask the question. What is the GK dimension of a module here? So I take some module M, which is finitely generated over the Weil algebra A and K, and the famous inequality of Bernstein says that GK dimension of this is should be on my slide. Is this inequality? The non-zero right module finitely generated over Weyl algebra n. GK dimension is at least n, which is half the GK dimension of this algebra. So now this is an important result because it allowed Bernstein to resolve a question posed by Gelfand in late 1950s. So the similar questions were asked for other classes of algebras, particularly for the enveloping algebras and also for rings of differential operators. Because this there's a Weyl algebra is the ring of differential operators over the polynomial algebra. So so it was found that for the same result holds true for the universal enveloping algebra also. This is UG, and G has some assumptions. It's a finite dimensional algebraic Lie algebra. And then this inequality was also shown to hold for the GK dimension of a module is at least half the GK dimension of the ring. Was also shown to hold for so-called rings of differential operators. Now, the question is, what is the use of this inequality? First thing is that in the case of Weyl algebras, this modules over Weyl algebras opens the door to a new theory, which is called the D-module theory, as you know, So in that theory, which has applications to partial differential equations. In that theory, central concept is a concept of a holonomic module. Holonomic module is simply a module over this algebra whose GK dimension is n. So in other words, it is at the bottom end of the spectrum. That is the least possible value for a finitely generated module over the Weyl. So such a module is called holonomic. And holonomic module always has finite length. And this result holds for an arbitrary algebra. So if we can extend this definition, in the case of Weyl algebras, of course, holonomic is defined as module with GK dimension equal to n. But if you have an arbitrary algebra, you can define the notion of a holonomic module, and then under reasonable assumptions, you can prove that the module is holonomic. A holonomic module has finite length. So this is an interesting result. Okay, but there are other classes of algebras for which so J.C. McConnell has constructed examples of algebras that occur as homomorphic images of enveloping algebras of Thousand Lie algebras having Gelfand Kirillov dimension n, but the simple module of GK dimension 1. So actually there was a belief in the 80s that simple modules will always be holonomic. Means that if in this if this m is supposed to, we assume that this m is irreducible. If it's simple, then the GK dimension equal to n will hold. It should be holonomic. But that was counterexamples were found later. So this belief is no longer. So this doesn't hold true. So when McConnell constructed some algebras which were having Gelfand Kirillov dimension n, but they had a simple module of GK dimension 1, Gabula introduced the notion. Why is it that some algebras satisfy this kind of inequality? GK dimension is at least n, or it is bounded below, by some integer. But for some algebras, for certain algebras, we can find simple modules of GK dimension 1. In his investigation, he introduced the notion of a filter dimension. Filter dimension is defined in terms of the filtration. It's defined in terms of the rating function, and what he showed was that for a finitely generated module over algebra A, the GK dimension of M is bounded, satisfies this inequality. It's a quotient of this by the dimension in maximums. So if the filter dimension of A is 1, then this thing becomes 2. This denominator becomes 2, and we recover the inequalities of Bernstein and the similar inequalities, Bernstein type inequalities for other classes. So we can always, for a given algebra, we can always calculate the filter dimension and use this inequality to get the bound on the GK dimension. But this filter dimension also need not be easy to calculate. For the Weyl algebra, as you would expect, it's 1, and same for the ring of differential operators over an affine irreducible algebraic variety. Smoothness assumption also is there. Okay, so we consider an example. We take this field F and we define this Laurent polynomial ring in n-1 variables. This is just a group algebra of the free abelian group on n-1 variables. And we define this skew polynomial ring Rn over Kn-1. And we define this, this is a kind of toric automorphism of Kn-1, and we define it like this. So this Q-Laurent extension is always given with respect to an endomorphism. So in this case, we take sigma to be this endomorphism of this Laurent polynomial. Now, also we make the assumption that the lambda I, these scalars, they are multiplicative, they are independent in the multiplicative group of the field. That means that they don't satisfy any relation of the form lambda 1 m1 up to lambda n-1 is 1 for non-trivial m1 up to n-1. In that case, we can ensure that this ring Rn, which is a skew-Laurent extension, has center equal to F. And it's also simple. It's a simple ring. So this is an example of a simple ring. Kn-1 itself is not simple, but Rn is simple. For this, it was known that the filter dimension is between n by 2 and n, but the exact value is not yet known. So this means that this filter dimension is between n12 and n. So let us examine how. Okay, if the filter dimension is big, for example, if it's greater than 1, it would mean that this denominator is big, and the denominator is big means that the lowest possible value of a finitely generated module will be small. So suppose we want that, suppose the algebra A has a module of small GK dimension like 1 or 2, and the algebra itself has GK dimension that's GK dimension is n can be any large number. But suppose it has a module of GK dimension 1, then one would expect that the filter dimension is denominator is big, and so in the case of this algebra, which is this Rn, we know that the filter dimension is big, so it is between n on 2 and n, somewhere between this. and if we put n on 2 in this inequality, then we get 1. That means that that already we know that it is possible that one-dimensional module can exist, and I mean one-dimensional module in the sense of GK dimension. And we can verify. We can actually construct a simple module with GK dimension 1, which is this. But we can also show that. We cannot find any module with GK dimension less than 1, because that will be finite dimension. So this is a suppose A in algebra is module M, which is finite dimensional. Then there is a natural map from A to the endomorphism algebra of M. So if this M is finite dimensional over K, then this is just some matrix algebra, which is also finite dimensional. And if this algebra A is simple, then this means that this map is an embedding. So A being infinite dimensional, it contains this example. A contains the group algebra of a 3 billion group, so it can't be finite dimensional. It can't embed in this. Therefore, we cannot have dimension 0. So in this case, we can say this module, I mean GK dimension 1 is holonomic, and then we immediately know that it has finite length. Finite length means that it has a composition series. So now for this algebra, we can also ask the question. For Rn, we can also ask the question whether it has a non-holonomic simple module. So the answer is given by this theorem. It says that the GK dimension of a simple module is always either equal to 1 or n minus 1. And for each of these values, there is one simple module having that value. So in between these two values, there is no. In between these two values, there is no simple module with that value. So if I say n is 4, n is 5, then this is 1 and 4, and if I take a value between that two, I cannot find, there does not exist any simple module with that value. And this next example is very much related to our earlier ring Rn. Kn minus 1 is the same. It's a Laurent polynomial ring in n minus 1 variables. Here we are having a differential operator ring because delta, this is an extension of this ring. In the earlier case, we are extending it by an automorphism, using an automorphism. Here we are extending it in a different way using the derivation. And derivation of the derivation of Kn minus 1 we define like this. So then McConnell had asked this K, the base field K here. So if you go back to the definition of K minus 1, it is defined over a field K. So this should be little k. Let's say little k is assumed to have characteristic 0, and in the last example we assumed that the lambda j, the parameters lambda j, they were multiplicatively independent, so they could not satisfy this relation. That we assumed to ensure that the ring Rn is simple, and in this case, if we assume that the lambda I they are linearly independent over the rationals, then this is a simple ring. So it was asked by McConnell whether so he constructed simple modules over Tn. He constructed simple modules over this ring Tn having dimension 1 and n minus 1, and he asked the question whether there exists a simple module having an having GK dimension between 1 and n minus 1. And that question was, we recently showed that this is not possible. There is no simple module between having GK dimension between 1 and n minus 1. Consider close related algebras. So now we are coming to quantum groups. Quantum groups provide us important examples of non-commutative rings. So how are quantum groups defined? They are usually defined as deformations of coordinate algebras of coordinate rings of algebraic varieties. So if you take the torus, this is a torus, and its coordinate ring, as you know, is this Laurent polynomial ring. We are quotienting, so the quantum deformation is obtained by, in this case, corresponds to quotienting the Laurent polynomial ring in n variables by these relations. So what we are losing in effect, we are losing the commutativity of the variables hi and hj. So these are called quasi-commuting variables, and this is becoming an important topic in this Q deformation. It's becoming an important topic, as you know, because now we have all Q versions of everything. We have Q versions of hypergeometric series. We have Q versions of analysis. We have Q versions of harmonic analysis, and so on. So, so this is basically the Q version of the polynomial ring, or the more precisely the Laurent polynomial ring. Now, so one of the things that we have studied about in the GK dimension is that how does the GK dimension of modules over the quantum torus behave? So one is this result which says that if this is a quantum torus algebra over field K, and GK dimension is n and curl dimension is n minus 1, and the center is GK dimension zeta, then for a finitely generated module over this, GK dimension satisfies this inequality. So one can ask that why not just calculate the filter, because already we saw that there's filter dimension, and we can calculate the filter dimension of these algebras, and that can give us bounds in the GK dimension. But as I also pointed out, the filter dimension is not easy to calculate always. So this gives us inequality. And there's another theorem that says that if a module is finitely generated over a commutative affine subalgebra of the quantum torus, so the module, this is a module over the quantum torus, and we are assuming that it's finitely generated over a commutative affine subalgebra. And we don't know, so this is an open question. The commutative subalgebras of non-commutative algebras, in general, they play an important role, and we don't know for quantum torus if commutative affine subalgebra is always so a commutative subalgebra is always affine. We don't know. This is an open question, but if we assume that the algebra is affine, then this commutative subalgebra is affine, then M is going to be torsion free over that affine subalgebra, affine commutative subalgebra, and the GK dimension will be equal to the transcendence degree, and it will be cyclic and also have finite. So, as I already mentioned, that an application of GK dimension is the calculation of curl dimension. It is otherwise not easy. And for this quantum torus, we consider the algebra tensor product. So just as we take any algebra, K algebra A and another K algebra B, we can always tensor them and get a new K algebra. So we can take two two quantum torus algebras, and we can take the tensor product, and the result will again be another quantum torus algebra. And then we can ask about how does this GK dimension and Kroll dimension in the non-commutative sense behave with respect to tensoring. So for GK dimension, the answer is easy. It is just additive. So GK dimension is just a sum of these. But Kroll dimension, it's not always a sum. And we have shown this inequality that the Kroll dimension is bounded by this, these two numbers, where G1, N1 and N2 are numbers coming from here. So we are, this is N1 torus and this is N2 torus. Means that it is a Cartesian product of N1 copies of K cross. K cross is just non-zero elements of K. So it is bounded by these two numbers, where G1 and G2 are the Kroll dimensions of these numbers, these algebras. So this gives us an upper bound, and thank you for that.
Okay, so I would like to ask, does there exist any example of a finitely generated infinite dimensional division algebra of finite GK dimension, which is also a division algebra? I mean, just add the condition finite GK dimension to the division problem of kudos.
I don't know of any example in which you have a division algebra which is infinite dimensional and also has finite GK dimension. All the rings that we get from localization, like the wild division rings, and these rings are all have infinite GK dimension, and also you want infinite dimensional.
Yeah.
So yeah, so I don't know of an example.
Okay, so I mean, is this problem considered, or I mean, is there any?
Yes, of course. This is an open question.